So in our next section then, we're going to talk about the Border Gateway Protocol, or BGP, which is mainly used for routing on the internet. So anytime that you have a connection to an internet service provider and you send your IP traffic out to them, they're using BGP in order to figure out what's the path that it takes through the internet. Specifically, the version that we use today is BGP version 4. Just like OSPF and a lot of the other protocols that we talked about, it is a standards-based protocol. There's a bunch of RFCs that define it and the more specific features of it, but the main one is 4271, which is a Border Gateway Protocol version 4. So again, if you want to see the real detail behind it, like the packet level format, how does the neighbor state machine work, how does the update state machine work, that's where you would find that really detailed information about it. There's a couple other books that are really good on BGP. The main one is called Internet Routing Architectures. And this is a little bit older. The publication date, let's see, is 2000. But still, the main features of BGP haven't changed in the past 10 or 15 years. So this book is just on BGP. A lot of it is just the theory of how internet routing works and why BGP was used to solve the problems that they ran into with internet routing. The other one is Routing TCP/IP Volume 2, where Volume 1 again talks about the IGPs like RIP, OSPF, and EHRP. This one focuses on BGP and multicast and some other miscellaneous topics. I think this is where he covers IPv6 as well. But both of these volumes, Routing TCP/IP Volume 1 and Volume 2, these are probably the best books out there for how the routing is implemented in Cisco IOS. So specifically, BGP is considered an exterior gateway protocol, or an EGP, where the other protocols we talked about up to this point, RIP, OSPF, and EHRP, those are considered interior gateway routing protocols, or IGPs, where the main difference is that BGP is used to route traffic between autonomous systems, or what's sometimes considered inter-domain routing. That if you have your network connected to a service provider, let's say you have connections to AT&T and Level 3, when you go to send packets to them and you want to make a decision, which provider do I send my traffic to, usually this is going to be based on BGP routing. BGP is also considered to be a path vector protocol. So it's not distance vector, it's not link state, it's its own type of protocol because it uses multiple attributes, or essentially vectors, that are used to decide how we're going to route traffic from point A to point B. We'll see that one of the main differences between BGP routing and IGP routing is that these attributes are what really gives BGP its flexibility. That BGP is used to enforce a routing policy, where we can decide on a per prefix basis how do we route our traffic to get there. With IGP, it's much more difficult to do this because when we look at OSPF or we look at EHRP, the attributes of things like the cost value or the metric value, those are not attributes of the routes themselves. Those are attributes of the links that are connecting you to get to those routes. So this means that you cannot change the metric of an individual route in OSPF. You can change the metric of the links, but then it's going to affect more than one destination. But in the case of BGP, each of the individual prefixes, or what we consider our network layer reachability information, or the NLRI, we'll see that these have a lot of detailed attributes that we can change in order to affect how the router is going to do its path selection, or sometimes what we call the traffic engineering. It is also a classless protocol, which means that it supports both variably length subnet masking and summarization. And summarization in BGP is one of the big key points about its design. That to try to keep the size of the internet routing table small, we need to make sure that we're not advertising thousands of /32 routes out to the internet. And you'll see that when you actually go into what's known as a peering agreement with your service provider, it's basically a policy that you have to follow when you advertise routes to them and when you learn routes from them. Part of the peering agreement says what is the length of the routes that they will allow you to advertise to them. Some providers would enforce an aggregation policy that says I'm not going to accept anything that's greater than like /18 or maybe /20. Some providers may be more lenient that say I'll allow /24 or /25 to be received from you. Really depends on where their situation is in terms of connectivity to other providers. But the idea is that if everyone was advertising their individual /30 subnets or their /28s, then the size of the routing table is going to get too big. So this is one of the big key points about BGP design, is to try to keep the table as small as possible, but yet be able to still make an informed decision about where I'm trying to send the traffic. Now, we looked at this a little bit earlier, the different routers that are available in the internet that are known as the route servers, or what is sometimes known as the BGP looking glass. And the BGP looking glass project basically is an agreement between different types of service providers that say, if you are advertising routes to me and you want to figure out how me and my customers are going to reach you, the only way you really have visibility of that is to log into my network and figure out what do the routes look like from my point of view. So if you search for this, either the BGP looking glass or the BGP route server project, they basically talk about the same thing. And you'll see that there's a large list that different people maintain about what are the different providers and what are their the addresses, or basically the DNS names of their looking glass servers or of their route servers. So you would see in this list like different providers like Cable and Wireless, or Cogent Communications, or Level 3. Pretty much all of the Tier 1 providers in the internet, like AT&T, Level 3, Quest, they're going to host these servers that you can log into and then do different verifications on what the routing policy looks like. So if you actually want to see what the routing table on the internet looks like, mainly the way that you can do it is that if you connect to the domain name either route-views or route-server dot the domain name of the provider, like here would be one for Global Crossing, and this is one of their views of from the European perspective. So these routers are physically somewhere in Europe, and that shows that portion of the global routing table from their perspective. So from here, you're allowed to do things like show IPBGP summary or show IPBGP. Some of the routers will have more strict policies as to what commands you can run. But when you look at like a show version, I'm not sure if this router will allow us to do it. This one doesn't. But let's say like one of the main ones is the University of Oregon. If we show IPBGP summary on this one, what it shows you is what are the different routers that it's participating in routing with, what are their different autonomous system numbers, or their ASNs. This is the public identification number that they use to determine how do you route traffic to them. Like this one here, 7018, this is AT&T. What this output shows that this router is peering with AT&T. It's using BGP version 4. And right now it's learning about 375,000 routes from that router. So essentially what the BGP table is going to do, or the BGP process, is that it's going to learn all of these different routes from different providers. It's then going to run a path selection process on them to figure out which ones do I actually want to use. These are the ones that would finally go into the routing table. So if we show IP route on this router, we should see basically that every possible destination in the internet is listed there. If we were to show IP BGP, this is the command that's going to show us what are all the possible paths and why are we choosing one versus another. So let's say we look at what the current address we're using here is. So when our traffic is routing out to the internet, whatever pool that we are being network address translated to is this one. If we were to then look at that route server and say show IPBGP for that specific prefix, it says that this router is using a /18 to reach us. There are two possible paths that it has to reach us. One of them is being learned from the autonomous system number 8075. One of them is being learned from 19 to 14. These numbers here then are going to say what are the different what are the different autonomous systems that the routes had to pass through in order to get back to us. So whoever is doing the local internet access here then is AS number 33650. This is where the route is originating from, or where the route is coming from. So what we're going to be focusing on today is how do the routers build the relationships in order to exchange this table. Then once the table is exchanged, how do they go through the path selection process to choose one route versus another? And then how can we change these different attributes that make up the routes, like things like the local preference, or the autonomous system path, or the multi-exit discriminator. All these different attributes of the route go through this long list of decisions that the router does, ultimately to try to figure out which one goes to the IP routing table. And this ultimately then is going to control how you forward traffic to that destination. Specifically, when we look at the definition of an autonomous system, which is what BGP is trying to do, is to route traffic between the autonomous systems. The key term here is that the autonomous system is going to be a set of routers under a single technical administration. So basically, for your enterprise network, if you're managing everything, normally those routers would all be grouped into one single autonomous system. Some networks, if they have very large, complex topologies, they might have multiple autonomous systems that are assigned to them. Typically, where this happens is that if one network acquires another one, like one service provider buys multiple, tier 2 providers or something like that, you may see that you actually have multiple autonomous systems within your network. But in order to reach or to get traffic from one point of the network to another, we would then have to use this autonomous system routing, or the inter-AS routing, in order to get the traffic between the different portions of the network. So this here, RFC 4271, this is the one that is the BGP v4 specification. But this is the main idea, that we're trying to route traffic between networks that are under different sets of administration. Where if the network is under all of your administration, usually the traffic is routed through IGP, like OSPF or EHRP or RIP. But between the autonomous systems, I don't run OSPF with AT&T, or I don't run EHRP with level 3. I'm going to have to use BGP to get my traffic to them. So to do this then, the first thing you would need to do if you are routing BGP is to get an autonomous system number. Just like IP address space or IPv4 or IPv6 address space, this is controlled by the Internet Assigned Names Authority, or IANA. And if you look at their website, iana.org, this is where you would fill out the paperwork in order to actually get assigned an autonomous system number. So once you get that number, then you can participate in routing with the different providers. Question?
Usually you get it from your service provider. They'll give you a form and you fill out, and then they submit it for you, right?
You can do it either way. We'll talk about both. Specifically, there's two different formats that the autonomous system number uses. It used to be a 2-byte field, which was 0 to 65,000. But now it's been extended to be a 4-byte field to allow for additional growth in the internet. Usually this is denoted as 2 decimal numbers that are values of 0 to 65535. This is called the AS dot notation, because it's easier to look at these 2 values separately than to look at a 4-byte number in decimal, because the value can be really, really large. What this also allows you to do is have a clean backwards compatibility with the original autonomous system numbers. So if I was allocated AS number 100, this used to be the format of my AS, but now it's actually 0.100 in the 4-byte format. So the vast majority of routers that run BGP, they should now be running code that supports these new 4-byte numbers. And you would see this when you look at the AS path information, or the autonomous system path information in the internet, that some networks will have 2-byte values, some will have 4-byte values. But the key is that this is just trying to identify from the internet's routing table perspective which routes are controlled by that particular network. Now, the reason that we want to run this protocol to begin with is that when we compare it to IGP, BGP is much more scalable. Where IGPs typically can route networks of thousands or possibly tens of thousands of routes, BGP is designed to handle hundreds of thousands of routes, or eventually as we grow to IPv6, there's going to be millions of routes on the table. So if you were to take the full BGP table and advertise this into your IGP, IGP is not going to be able to handle it. There's simply not enough memory allocated to the process, and the path selection is too complex to run a shortest path first calculation throughout the entire internet, or to use EHRP's feasibility condition to try to figure out every possible destination. So this is the main idea of BGP, that it's going to be more scalable than the IGPs, but it's going to add the scalability at the expense of different features like high availability or convergence time. So BGP is going to take longer to figure out there's a change in the network and to reconverge around that versus your IGPs, because we simply can't run path selection as fast as possible on 400,000 routes versus our 1,000 or maybe 10,000 routes internal to the network. The other key is that BGP has to be stable. The internet routing table actually never converges, where if you look at any of these devices in the BGP table, and if we were to look at one of the route servers, when we look at the show IPBGP, and actually the show IPBGP summary, we'll see that constantly from its BGP peers, or basically the routers that it's running BGP with, if we were to look at this messages received field, we're going to see that this number is constantly going up every time we look at this show IPBGP summary. Basically, this means that we're constantly receiving updates from these peers, and we're constantly having to recalculate the table. If we were to look at the CPU of this router, the vast majority of the time that it's using the CPU is going to be for the BGP calculation. And the reason why is that not only do we have 400,000 routes, we actually have 12 million paths to reach them. So when it's making its decision, it's doing this based on 12 million possible paths. Then it says, out of this, I chose that there's actually 400,000 unique entries. These are the ones that ultimately go into to the routing table. So these are the two main goals of BGP. It has to be scalable and it has to be stable. We need to make sure that we can run the path selection while at the same time actually routing the traffic. Where protocols like OSPF typically can't handle this, because when you run SPF calculation, it's changing the path selection for all routes. So when one route changes, you have to start to drop traffic for a short amount of time while the network reconverges. The idea of BGP is that you can't do that. You want to reconverge the routes that have changed, but for the ones that haven't changed, you need to continue to do forwarding for those. Question?
I guess I didn't understand. Never converges the routing table in BGP?
The routing table is constantly changing in the internet. So if you look at it at a current time and then look at it 5 seconds later, it's going to be different. So for all the time, you're constantly receiving updates about changes in the network, because figure there's millions, tens of millions of devices that are connecting to the internet. All of their addresses are somehow advertised into BGP. So since there's so many different networks connecting, there may be some guy in Australia right now that shut down his interface, means that the BGP table is going to have to reconverge around that. So the table is constantly changing.
So the table's never in sync?
The tables are never in sync, correct. The other key feature is that it's going to allow us to enforce a routing policy. That if we compare IGP, that typically uses a cost value applied to the link, it's not very feasible to change path selection for individual routes, because typically multiple paths are going to be using a single link in the network. So if I change the cost of my gigabit Ethernet link, it's likely that there's more than one destination that's using that same link. So they're all going to inherit that cost change. Where in the case of BGP, the attributes are a function of the individual routes themselves. So I can change how I'm reaching one network versus another one, and it doesn't really matter what are the physical links that I actually use in order to reach that. So traffic engineering is definitely one of the main features that you use to change how traffic is routed in your network with BGP.
So in comparison to IGP, is there a topology so to speak, in BGP as such? Like, is there?
There is a topology table. That's what the BGP table is. When we look at the show IP BGP, this is the topology. This is basically the database. But the difference is that each of these routes have individual decisions done. When we compare that to OSPF, we had the logic of things like, if I'm trying to reach an external route, let's say I have the external route 10.0.0.1 that is via router 1, and then router 1 is reachable via my ABR, that is router 2, and router 2 is reachable via my shortest path tree via router 3. You have this hierarchy of how the internal logic points back at itself, where the problem you run into is that if the path to 3 changes, it means that the path to 2 and the path to 1 changes. In BGP, there's no hierarchy like this. You simply say that I have 10.0.0.1 via whatever the next hop value 1, 2, 3, 4 is. This decision is then going to be completely separate from anything else that's going on in the network.
So is there an algorithm?
There is an algorithm that it goes through, and that's one of the things that we're going to focus on today is how does it actually choose the paths, and then how can you change those values to get it to choose a different path versus what it's currently doing. Now, the reason why you would need this to begin with is mainly for 2 reasons. One is that you are a transit provider, like you're an actual service provider that is selling bandwidth to customers. If you don't have the correct copy of the routing table, you're not going to be able to make the correct decisions. So typically a service provider like AT&T or Quest, you wouldn't see default routes in their network. They're going to have an exact match for every possible destination in the table. And if you don't have that route, it means it's not supposed to be reached via the internet table, and that traffic should be dropped. The other case would be if you're an end customer, but you have multiple connections to service providers. So if you're an enterprise edge, and I'm going out to AT&T, I'm going out to British Telecom, and I want to change how my traffic comes in from them, I can use BGP to do this. Otherwise, if I was just using default routes out to them, it's not going to be my decision how the traffic actually routes. It gets into their network, and then they make the decision. So you would see there are certain cases that you don't need BGP in your network, and you wouldn't want to run it. If I only have one connection to the internet, then BGP is going to be overkill. There's no reason to run it. You would just default your traffic out to the provider and then let them worry about the routing decision. But if there's multiple links and you want to control how the traffic enters the network and how the traffic leaves, that's mainly what BGP is going to be designed to do. This type of topology would be an example of what a transit network is. If we are ISP1 and we are assigned autonomous system number 1000, and I want to get traffic from customer 1 up to the internet, when their traffic comes in, I'm going to need to make this decision. Do I want to go this direction or do I want to go this direction? For this reason, I cannot use a default route. Otherwise, maybe I send my traffic to ISP3 with a default. There's nothing stopping them from pointing a default route back at me. And we want to try to avoid these type of looping logic problems. So if we agree that no one is going to have a default route in the internet's table, then the traffic should theoretically always be routed correctly to where the destination is located. It would be okay for the end customer to use defaulting because they only have one physical path out to the rest of the network. So I could say from customer 1's perspective, just get my traffic to the ISP, then it's up to them to make the decision. The case where the enterprise network would not want to do this is if they're multi-homed, or basically if they have multiple connections to different service providers. So if I'm the end customer and I have connections to AS1000 and AS2000, I may want to make a decision that it says, maybe if the customer is located here, let's say Google's web servers are directly attached as a customer to this ISP, maybe I want the traffic to go that way as opposed to going this way. And if I were simply to use default routes, I have no control over that.
Can you use policy routing?
You can use policy routing, but from a large scale point of view, it's not very efficient. Because you would have to look at what's the destination that you're trying to reach anyways, and then do a manual policy change on that. So you could theoretically use it, it's just not very scalable to do that.
This applies to MPLS, layer 2 providers?
This, from our perspective, we don't care if they're using MPLS. So they could be using MPLS to get the traffic between us and somebody else, but it's going to be independent of our view. In a lot of cases, there's separate services where MPLS would be used to replace your private circuits. Like if you had a frame relay network previously that was going between router 1 and router 2, the service provider previously was doing layer 2 circuit switching to get the packets between them, but maybe now we upgrade to a layer 3 MPLS circuit. The logic here is that still I'm trying to get traffic from router 1 who's inside my network to router 2. A lot of times when you buy MPLS service, what the service provider will do is give you either a different physical link or a different like sub-interface to say that you need to use this interface to get to the internet. Because from their perspective, they're going to be two separate routing tables. They have a routing table that's used to get traffic between your sites, and then a routing table that's used to get to the internet. And this is mainly what BGP is going to be used to do, is to maintain the internet's routing table. Now, the cases where you wouldn't want to run BGP is mainly when you only have one service provider. So in that case, I can just use a default route. The traffic is going to go to them anyway, so I just get my packets there. They're going to make the routing decision. The other case is when your platforms have limited resources. Typically, it takes a lot of memory and a lot of CPU to run the BGP process, because when we look at one of these routers that's using the full table, if we were to look at the show memory, it says right now that it's using 1.5 gigs of memory just to hold the table. So this is not going to be included basically in any of its forwarding features. So as you start to add other things, maybe you're running the firewall feature set, or maybe you're doing IPsec VPNs, then it's going to be really taxing on the platform to hold the table, plus to actually do the routing features.
So this usage is related to the size of the table?
Related to the size of the table, right. And you can see this when you look at the show IP BGP summary. Now the router is probably going to be doing some other minor operations, but these route servers, they're not actually used for forwarding. So no one's data traffic is actually going between their interfaces. They're just used as a view of the control plane. So this is why they allow you to log into it, because even if the router crashes, it's not going to hurt anything. It's just used to view the routing table. But if you were to take these entries, you can add these individual values up. How much are the network entries taking in memory? What are the path attributes taking up? What is the number of AS path entries taking up? But if you add all this up, BGP takes a lot of memory just to hold the table.
Is there, like, if you use BGP to your ISP, is there a way to filter the table so you don't take?
There's a way to filter the table, and we're going to talk about that as well. So what you can do in cases like that, where you want to run BGP, but you don't want to hold the full routing table, one of the typical things that you can do is say that if I'm AS1 here, and I'm connecting to my ISP, maybe they're AS2, and they have some directly attached customers. They have AS3 and AS4. These are direct customers of them. Then I have some other provider. I have AS1000. And I know that they have other customers. So this is ISP2, this is ISP1. Maybe they're connecting to 1001, 1002. Then behind them is the rest of the internet. One of the common filters that you can do in BGP is to look at how many numbers of autonomous systems the route passes through before it reaches you. So if I were to figure that any routes that I'm learning from my provider, if the route actually exists in their network, like let's say they have some sort of mail server or web server that's hosted there, when I receive those routes, what's known as the AS path, which is one of the attributes of the route, this is going to say 2. which means the route was originated in AS2 and I'm learning it from AS2. For any route that is originated by AS3, when I learn this, it's going to say the route originated in 3, then it passed through 2, and then it got to me. The AS path information would say 2, 3, meaning I learned it from 2 and it originated from 3. The routes that are coming from 4 would say 2, 4. On this side, the routes that are coming from 1001 would say 1001, 1000, 1000 being at the front, or 1000, 1002. So one of the basic filters you can do is to say, look at the AS path length. If there's exactly 2 ASs in the path, it's coming from someone who's attached to my service provider. And you would figure that if I'm using level 3 to reach the internet and someone else is using level 3, it's probably a pretty good route to use them for my traffic to get to them. And the way that you do this, and we'll look at this in more detail, but the way that you could do this is that the router matches on a string, which is known as a regular expression. And you could say, basically a search of characters. If we were to say, look for the regular expression that is any number that goes from 0 to 9. So this says, look for a range of characters that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There has to be more than one instance of that. So this would be a collection of numbers. Then this would happen again. There are specific characters that are used to denote where does the string start and where does the string end. But this combination would say, look for 2 autonomous system numbers. I don't care what they are, but it should say that the length of the AS path is 2. So what this result is that whoever this router is peering with, these routes are ones that are coming from these service providers' customers. And when you look at the whole of the table, this is going to be a lot less routes than the full table. So this is one basic logic you could use, that if I don't have enough resources to hold the full table, maybe I want to hold just part of it, where I'll take 1 or 2 ASs deep and then I'll use a default route for everything else. It should give you a fairly good visibility of where you want to send the traffic.
So this is control views and attribute?
It's the attribute that it's looking for is the autonomous system path,
Okay.
which is this number all the way on the right here. So each of the routes, this is one of their attributes, which is the AS path. Show IP BGP REGEXP. This is to check a regular expression. Then we'll see once we actually implement this, the way that the filter is applied is that the router creates what's known as an AS path access list. The AS path access list says to look for a specific string, where I would use maybe this string that I used here, and I say permit 2 ASs long or 1 AS long. And then when I configure the BGP process, I would say if I have a peering to the ISP and their address is 1234, use this list 1 to filter out routes as I'm receiving from them. Basically what this would say is that when they're sending me updates, I'm going to sort through the attributes and I'm only going to accept ones that have 1 AS in the path or 2 ASs in the path. From that particular neighbor. So there's a lot of different ways that you can do this, and this is why BGP is so flexible, that it's designed specifically to implement a policy. So there's tons of different attributes that we can filter on, there's tons of different attributes that we can change, and this is one of the main focuses of understanding BGP, is to figure out how these different attributes work and how you can change them to enforce a specific policy that you want.
So what you just did there with that one is the neighbor is the ISP in theory.
The neighbor is the ISP.
The bottom one is just saying only accept routes
from the ISP, right. So this is the ISP's route. This is their customer's routes.
First, your ISP's AS number is not going to change, so you could just specify.
You could match their exact number as well, right?
There'd be another way to do it, to say routes of AS2 or the directly connected AS.
Right. So there's lots of different ways that you can match these strings, and we're going to go through some of this logic. But the key is that BGP is very flexible, and you may literally find that there's 100 different solutions to get to the same result.
So outbound filter list, right, where rather than receiving 1 million routes and then sifting through for the 20 that you want in your table, of course you could send if your ISP will dance with you, so to speak, send him an outbound filter list. And just
You can,
these routes.
right? Yeah, yeah. So this is one of the other reasons why you wouldn't want to run it, or maybe that you couldn't run it. If you only have maybe layer 2 switches on the edge of your network and they don't have a lot of memory, then they're not going to be able to handle the BGP table. Typically, Cisco's going to recommend at least a 1 gig of RAM just to hold the full table. The other reason would be that if you don't have your own IP address space, that when you get a circuit from your provider, if they're assigning you their address space, which is considered non-portable, or what is the opposite of provider-independent space, or what's known as PI space, there would not be a reason to run BGP, because you can't take address space that belongs to AT&T and advertise it to your other provider. So this would be the case, like let's say you have a cable modem, you don't actually own the address that you're using to send the traffic out to the internet. So the way that you have to get the addresses is to get the assignment from IANA. So if the service provider is the one that is giving you the space, they're not going to allow you to advertise this to other autonomous systems. And that's part of the BGP peering agreement. Because what they don't want to happen is that if, let's say the space is the 20 network. Okay, the 20 network is usually the ones that's assigned to the cable companies, like Comcast or other cable providers. So if I'm peering with Comcast and I am AS1, when I send my traffic in this direction, I'm performing a network address translation that goes to whatever number they're telling me to use. Like maybe my address is 20001. Then if I go to another provider, maybe I have like AT&T DSL. Whatever address they're assigning me, let's say it's 30001, their customers can't route this direction to reach this address, because they're not going to be allowing this advertisement to be received. So it means that the address space on this side belongs to Comcast. It doesn't belong to me. The address space on this side belongs to AT&T. It doesn't belong to me. So the way that you would need to fix this in order to run BGP is tell them, I don't need your address space. I already have my own. And I got the allocation from IANA. They also gave me the AS number. Then we can form the peering agreement, and then I'm going to advertise you these particular addresses. Now, specifically, the way that BGP is going to work is similar to how the other IGPs work that we talked about, like OSPF and IS to IS, or OSPF and EHRP, where the first thing we have is what's considered the neighbor table. This is where we keep track of the adjacencies between the routers, or in the case of BGP, we call these the peering relationships. Peering relationship is basically just me sending you updates, you sending me updates, and we're going to run path selection on each other. We then have what's known as the BGP table. BGP table is going to be all of the possible prefixes learned from all of the peers. Then we have the final routing table. This is the routes that we're actually using, or what BGP calls the best routes. The idea is that we're going to be learning routes from the different peers. These go into the BGP table. We then run what's known as the best path selection on the BGP table. The result of this is the routes that are filtered out and that go to the final routing table. So when we looked at that router that had the full table, if you were to compare the output of show IP route versus show IP BGP, show IP BGP for this router was showing like 12 million routes. This one is showing somewhere in the order of 400,000, which is the result of figuring out of these 12 million possible paths, which ones do I actually want to use. And we can see these are installed as the status code B in the table. So the first thing then in the actual operation of BGP is to start these peering agreements, or these neighbor relationships. Once the neighbor relationship is up, then we can exchange the table. Once the table is exchanged, we run the best path selection and figure out which routes actually go into the table. So again, when we look at show IP BGP summary, this is showing what are the different neighbors. When you say show IP BGP, this says what are the routes that are learned from them. Then show IP route, this is the result of the best path selection. These are the routes that actually get installed, and those are the ones that are used for forwarding. So the next step would then be to figure out how do we actually start these relationships with the neighbors, or how do we establish the peerings. Just like in IGP, this is always going to be the first step. We need to start the relationship, then we can exchange the routes, then we can run the path selection. The difference, though, is that unlike IGP, BGP doesn't have its own transport. When we looked at EIGRP uses what for transport? It uses IP protocol number 88, which EIGRP calls the Reliable Transport Protocol. But the key is that EIGRP specified this itself. Where in the case of OSPF, OSPF uses protocol number 89, which is just OSPF. It's in charge of its own transport. With BGP, it uses TCP for transport. Uses port number 179. So this then means that for the routers to establish a peering relationship, they first need to have IP reachability to each other. This also means that the neighbors don't have to be connected, and they're not automatically going to be discovered. In the case of IGP, normally we're using a multicast address like 224.0.0.5 and 6 for OSPF, or 224.0.0.10 for EIGRP. This is going to allow the router to figure out automatically who wants to run the protocol. In the case of BGP, you don't do this. You say the neighbor statement. This tells the process to start a TCP peering with them at port 179. But this also means that the neighbors don't necessarily have to be directly connected. As long as I can use an IGP routing protocol, like OSPF or EIGRP, in order to establish the TCP transport, I can form the peering relationship and then exchange the routes between them. Where the most common case that you would see with this is that many designs for the enterprise network will have the customer edge routers form what's known as an iBGP peering with each other. This is an internal BGP peering. The link from the customer edge to the provider edge, this is where we form an eBGP peering, or an external BGP peering. In the vast majority of cases, these neighbors are going to be directly connected. So whether this is something like Metro Ethernet or whether it's a DS3 link, whatever the connection is, this is going to be some directly connected link between the neighbors. So these routers, these are out of our administration. This is going to be whatever our ISP is. But on our side, we have the edge routers that are running BGP, and then typically in the physical transit path, there's going to be multiple other routers here. The end result that we'll see is that these neighbors here, here, and here, they don't necessarily need to run BGP. As long as they can get traffic between the network edge routers, so from here to here, we can form this non-directly connected relationship because we're using TCP as the transport. If this were an OSPF routing relationship or EIGRP routing relationship, that wouldn't be allowed because that always has to be on a directly connected link. But BGP neighbors, they can be multiple hops away from each other. So to do this, to actually establish the BGP session, BGP has a couple different packet formats behind the scenes, where they're mainly going to fall into 4 different categories. We have the open message, the keep alive, the update, and the notification. The first of them, the open message, this is what we use to start the peering. So this is where the neighbors say that I want to run BGP with you. We're going to exchange a number of different attributes and say things like, what's your autonomous system number, what's your router ID, what are the other attributes that you have. And the keep alive, as you can probably guess, this is just to make sure that the neighbors are there. So once the table is finally converged, I'll send you a keep alive. You're supposed to respond to this. That way that we know that the peering relationship is still there. The update message, this is actually used to exchange the routes or the network layer reachability information. This is where I say I know the route 10.0.0.0/24 and it has this local preference value and it has this AS path information and it has this multi-exit discriminator. This is where the route plus its attributes are actually sent. The notification, this is for error reporting. If some reason your BGP configuration is wrong and it doesn't match what I expect, I send you a notification to tell you why the peering had to be torn down. Normally, you're not going to receive this unless there's something wrong with your configuration. This would be typically what you would want your management software to generate logs on and tell you if the router generated a notification because something wrong is in the network. Maybe somebody changed something that's now broken, or someone is doing some sort of attack on the BGP process. Because once notification happens, the routers drop the peering session, which means they're going to start dropping packets between each other because they're not going to have routes to each other anymore. So the actual peering relationship then is going to focus on this open message. This is where the routers tell each other different attributes like what's the version, which typically should be version 4, what's the autonomous system number, what's your router ID, what are the timers that you're using, so how often do you want to send hello packets, how often do you want to send the responses. One of the differences here between BGP and IGP is that this number is negotiated. If I say I want to use a keep alive timer of 10 and you say you want to use 5, we're going to choose the lower value and we'll negotiate it down to 5. Then we have what's known as the options or the capabilities. This is where BGP actually decides what type of information is it going to be advertising. The vast majority of the time, this is going to be used to exchange IPv4 unicast. This is our normal routes that are in the internet table. But BGP also has other applications that it could use. It could be used to advertise IPv6 routes. It could be used to advertise IPv4 multicast. It could be used to advertise VPN v4 routes for MPLS. Because BGP itself is not a routing protocol per se, it's an application that one of its jobs is to exchange routes. The actual routes that it exchanges, there's lots of different values that it can use for these. But the ones that we really care about are just the unicast routes. Most of these other ones, these are outside of our scope. But the point is that when the neighbors start the negotiation, if I say I want to run IPv6 routing, and you say you want to run IPv4, it's not going to be compatible, and they won't be able to start the peering. We then have the keep alive message, which is pretty straightforward. This is used just to figure out, is the neighbor there or is the neighbor not? If we were to set the hold time to be 0, the keep alives were disabled. Keep alives are disabled. What this would be used for is to ignore BGP for convergence and to use your physical link layer convergence. Where in a lot of cases, if I have an eBGP peering relationship to my service provider, and I have a physical link that's connected between them. Let's say I have an OC48 packet over SONET link. If this neighbor goes down, the layer 1 process of SONET is already going to tell me that the neighbor is not there. So it would then be redundant to use something like BGP to even exchange these keep alives. So in certain circumstances, it can be used to say, I don't need BGP for this type of error reporting. I'll use either my physical link layer reporting, or I'll use one of those protocols like the bidirectional forwarding detection to make sure that the neighbor is actually there. Because doing these keep alives is just going to eat up additional CPU cycles between the neighbors. And if the router is already under load because the BGP table is large, then you could end up losing these keep alives and then dropping the BGP neighbor relationship between them. So a lot of times in today's network, you don't really need the keep alives. They're not as important as they used to be. This is originally how BGP was going to do convergence, but now there's better ways to solve this in most networks today.
So if you were the CE router, you can actually set it to 0 and force the provider side to negotiate down to 0.
Correct, correct. But if you did that, you would want some other mechanism to figure out are they there or are they not. Because if I disable the keep alives, BGP has no way to know if the neighbor is up or not.
Oh.
So the only time you disable this is if you have some other mechanism that's going to do the same thing, which is like the layer 1 link protection, or the layer 2 protocol like bidirectional forwarding detection. Normally you can just leave these alone and it's just going to negotiate to the defaults of what the routers want. But the key is that this is just a basic keep alive that says, are you there? And then the other router responds. The update message, again, this is where we're actually exchanging the routes. So it's used to both advertise routes and to withdraw routes, or to delete routes. This is going to include the routes that I want to delete, which is the withdrawn list, and then the routes that I want to add or advertise. This is considered the network layer reachability information, or the NLRI.
Quick question. So you want to withdraw just one route. It's the update that's going to do that.
The update does it, and inside of it, it says withdraw this route. Then we have the actual attributes, which are sometimes called the path vector attributes. This is the specific things about the route, like the AS path length, or the local preference, or the multi-exit discriminator. This is how we actually decide which routes do we want to use and which routes don't we want to use.
NLRI standing for
Network layer reachability information. So it's a fancy way of just saying the routes. The other one we have is the notification. This is used just for error reporting. Most of the time, this is just going to be a configuration problem on your end or on the provider's end if you see this. So if I was trying to run IPv6 routing and they were trying to run IPv4 routing, you'd see a notification and it tells you that the capability is unsupported. Or if my hold time is too small and you don't accept that, you would send a notification saying the timers are not valid. This is also what the router uses to say, I no longer have received keep alives from you, and I have to tear the neighbor relationship down. This is typically what you would want to keep track of in your logs. That if a notification is generated, you want to know, because it means that your BGP peering is gone, and you're now no longer able to send traffic out to that provider. To actually establish the peering relationship, just like in OSPF or just like in EIGRP, the routers are going to go through a couple different states. This is what we define as the state machine. The details behind this is going to be what's listed in the BGP RFC. So in each of these documents, you would see what we're considering the finite state machine. And there should be a section here that talks about the peering state machine. Bless you. So basically, this is the different states that they go through as they're trying to establish the relationship. From our point of view, the specifics on this aren't really that important, because as long as you have basic transport and as long as the network is configured correctly, you should properly go through these different states. But specifically, the way that they work is that you start at idle. This means that you're waiting for someone to start the session. You're waiting to start specifically what we consider the TCP three-way handshake, where you have the TCP client and you have the TCP server. Since we're using TCP as transport, BGP behaves just like any other TCP-based application, like web browsing or like Telnet. Uses the same logic to establish the session. It says that the client is supposed to send the first portion of the handshake, which is what? The SYN. The server should reply back with the second portion, which is the ACK-SYN, or the SYN-ACK, saying, I got your packet, I know you want to start a session, I also want to start a session with you. The client should then respond back with the third portion, which is the acknowledgement. This opens the session, and now they can actually start to negotiate the TCP relationship. This is where you would see if there's a problem with basic IP reachability. If you're stuck at idle state, it might mean that the traffic is being filtered out between you and the neighbor, or that you just don't have a route to the neighbor. So we go from idle to connect. This is where we're now in the process of going through the actual three-way handshake. Once we get to active, this would mean that something is wrong with the handshaking process. Normally, this is going to be related to a transport issue. Like if for some reason I can send my packets to you, but you can't send them to me, I'm sending you the SYNs and I'm not getting the ACK-SYNs back, I know that then there's a problem with the transport. So typically what you should see is that you start at idle, go to connect, and then go to open sent. If you get to active, it means there's something wrong. Open sent means that the three-way handshake was complete. Now TCP is done. Transport is open. Now we can actually exchange the attributes to say, let's start the peering. This is now where the open message has been sent. The other side should then go to open confirm, basically saying, I got your message. Now let's actually negotiate the parameters. Then finally, we go to the established state. This is where the peering is complete. Now we can actually start to exchange the updates. So let's take a look at a basic example of this between two routers here. Let's say that we have router 1 and router 2 connected over a LAN segment. Router 1 is going to be 10.0.0.1. Router 2 is going to be 10.0.0.2. So on our router 1, let's go to the interface level. Make sure this is enabled and that it has an address. We'll say the address is 10.0.0.1. Router 2 is going to do the same thing. The address is 10.0.0.2. And we want to see, before we can establish the peering relationship, do we have basic IP transport between them? Okay, so 1 and 2 have reachability to each other on this, this segment now. The next thing we would do configuration-wise, just like the other IGP processes, is to run the BGP process, and we give it our autonomous system number. So let's say at this point they're both just using number 1. We'll get into in more detail exactly what the result of this in the configuration is, if it's the same or if it's different. The statement to start the process is the neighbor statement. So we say, what is the address on the other side? It'll say 10.0.0.2. A question? Then I need to specify what is their autonomous system number. This is the remote neighbor's AS. This is the minimum configuration you need for the process. Just to start it, we say router BGP, and then use the neighbor statement. On router 1, if we now look at the debug IP packet detail and the debug IP BGP, what we should see is that periodically router 1 is now trying to send TCP packets to this address at 179, trying to start the process. If we were to go to router 2 and do the same debugs, debug IP packet detail and debug IP BGP, we would eventually see that 1 sends a SYN, which we can see here in the debug IP packet detail output. It says the packet came from 10.0.0.1 going to 10.0.0.2. It is a SYN. It is a TCP packet that's using port 179 as the destination. This value here, the source port, that's going to be random. Router 1 sends the packet to 2. 2 is responding on source port 179, telling them I'm not running BGP. It's replying with an acknowledgement but a reset, basically saying this port is not open on me. I'm not running that process. This is simply because I didn't configure BGP on router 2 yet. So it's denying the relationship, saying I'm not running the protocol with you. So now on router 2, let's enable that as well. And I'll also say no service timestamps to try to clean up this log output a little bit. So router 2 says under the BGP process, I also have a neighbor relationship with 1, and they're going to be in autonomous system 1. Once both of the neighbors agree that we're going to start the process, now we go to the active state, which means that we're going to start to send the three-way, or start to go through the three-way handshake. Right now it hasn't been successful because it wasn't properly configured on both sides. So we should see that one of them eventually goes from idle to connect. From idle to connect, so now we're starting the process. It says that we received a packet in from 10.0.0.1 going to 10.0.0.2. The source port was a random value. The destination port was 179. What this means is that router 1 is the TCP client. Router 2 is going to be the TCP server. How can I tell that based on this output? Because the destination port is the well-known port when it's coming from 1. So since BGP is a standard TCP application, it's going to work just like web browsing does or like Telnet does, where if I'm trying to hit a web server and I am the web client, I'm going to start the three-way handshake by sending them a SYN. The source port on my end is going to be some random value. The destination port is going to be the well-known port. In the case of web browsing, it's 80. When the server responds with the ACK SYN, or the SYN ACK, their source port is the well-known value. Their source port is 80. The destination port is the random one that we negotiated. So in the case of BGP, whoever is starting the session, they're going to use destination 179. Whoever is responding to the session, they're using source 179. The reason that this is significant to note is that if you're doing any type of filtering in your network, you need to make sure to account for the port value both ways. So let's say that on your network edge, you're doing a peering to your ISP, but you also have an access list there to filter out traffic as it's coming from the internet. What you would need to do is to say access list 100 permit TCP any equal to BGP, but also permit TCP any equal to BGP any, because we don't really know who is the server and who is the client. They're going to automatically negotiate this based on basically who starts the session first. But I need to allow it from the client to the server and from the server back to the client. So it has to be the port values both ways, source or destination.
Do you apply that to the interface, or is there something within BGP?
It would be under the interface. So only if you're doing filtering at the interface level is this really going to matter. If you're not filtering out any of the packets, then it should be fine automatically. Okay, so now we have the session open from a TCP point of view. Router 1 sent the SYN. I replied back with the acknowledgement. So here's the SYN coming in. We see the ACK SYN. Then router 1 replies with the ACK. So now three-way handshake is open. The TCP session is open. This is what gets us to connect. Now we actually tell each other what are the specifics about the BGP peering. Router 1 says, I'm running version 4 of BGP. The hold time I want is 180 seconds. I told router 1 I'm also running version 4. My autonomous system number is 1. My hold time is 180 seconds. I then am going to go through this capability exchange. This is where the routers tell each other what type of routes do they want to advertise. This is broken into two values that is known as the address family identifier and the sub-address family identifier. AFI1 and SAFI1 means IP version 4 and a unicast. Basically what this means is that by default, they're going to try to run IP routing with each other. They're not going to run IPv6 routing automatically, or they're not going to run MPLS routing automatically. But for IPv4 unicast, they're assuming that's probably why you want to run BGP. If you're running it for some other reason, you can change that if you want to. Just the devices are going to do the capability exchange of this by default, AFI1, SAFI1. There's also some optional capabilities. It says this router is trying to advertise a feature that is known as route refresh. There's both an old version and a new version of this. I'll explain a little bit later what this specifically means. But what it's used for is that if I want to send you a triggered update, or I want to ask for a triggered update, this is what the route refresh capability does. Before this, the only way to force an update was to stop the TCP session and restart it. The problem with that is that you lose all of the routes. You have to learn them again, reconverge, and in the meantime, you start to drop traffic. So route refresh allows you to apply a new policy out or ask for a new policy in without having to drop your traffic.
Are you saying every time I lose my session with a neighbor, I have to rebuild the routes?
It would be rebuild the routing table, right. So if the TCP connection goes down, all of the routes that are learned from that neighbor immediately get flushed out of the routing table.
Okay.
So route refresh is the comparison between these two sites? What is it exactly?
It's asking for a triggered update, or it's sending a triggered update. When we actually look at the result of it, it'll make a little bit more sense. Now we go to open confirm. This basically means we agreed on the parameters. Here we would see the routers actually exchanging the updates, but right now there's no routes being advertised, so it doesn't show that. But finally we go to established, and then we get this log message saying that the BGP peering is up. At this point, if we were to look at the show IP BGP summary, we should see that there's an entry in the neighbor table or the peering table for this address. It says they're running version 1, they're in autonomous system 1. These are the number of messages coming in, these are the number of messages going out. This is the table version that I'm using with them. So as new routes come in, as new routes go out, these numbers are going to increment. This is what you would see on your actual internet routers, that the topology is changing. These numbers are going to keep counting up. If this number is staying the same, it means right now they're not sending any updates back and forth between each other. It says the neighbor has been up for 6 minutes. For your real routing adjacency, you want to see that this number is going to be as long as possible or as big as possible. So on this router here, when we show IPBGP summary, ideally it's going to say that some of these are up for weeks or months. So there hasn't been anything wrong in the TCP session between them for 7 weeks. Some of these have problems where the peerings are not working. This says active. This number here is how many routes are you learning from them. Right now in our case, there's no routes being advertised, so this number is 0. But in a real design, you would see this number is a large value. It's saying you're receiving the full internet table from them. Okay, any questions up to this point on the basic establishment of the peering? The key is that before we can do the peering relationship, the neighbors need to have IP reachability to each other, because they're going to use TCP for transport, which means that if I can't ping the neighbor, it's unlikely I can send them a TCP message and then get the response back in. In this type of case where the neighbors are directly connected, it's kind of assumed that if there's nothing wrong with the Ethernet network, we should have reachability. But in cases where the routers are multiple hops away, if there's a problem with your OSPF routing or there's a problem with your EIGRP routing, then the routers might not have reachability and might not be able to establish the session. The other way that you could test this would be to send just a low-level TCP connect message to the neighbor at port 179. So on router 2, if I were to say to telnet to router 1, telnet to 10.0.0.1 at port 179, if this opens, which just tells us that the three-way handshake was correct, it means that router 1 is listening for a BGP peering from me. If I had some other interface, let's say I had a loopback 0 with an address of 2222, if I source the telnet from this, I would get the connection refused, because router 1 doesn't have a neighbor statement that points at this address. The neighbor statement is pointing at 10.0.0.2. So I have to agree where your packets are going to come from, and you have to agree where my packets are going to come from. This is an added security feature of BGP, that you can't just accept updates from anybody. You have to pre-configure who is going to do the sending and the receiving of the routes. Question?
So in a scenario where you're dual home to your service provider, to the same service provider,
Right.
and you have routes to a destination from both routers.
Mm-hmm.
Now, both routes made it to the routing table, and you lose connection on one side of you lose your neighbor
Okay.
on one side.
Right.
Is there, like, how does it decide, or how does it need to calculate, or it's immediate? How does that happen?
So let's say that you have one ISP, right? But there's 2 different edge routers that you're peering with. Is that what you're saying? So on your side, you have router 3 and 4. So between these 2, there's an eBGP peering. Between the other side, there's an eBGP peering. Let's say that between your edge routers, they're running iBGP, to make sure that both of them know that there's multiple paths to the provider.
Right.
If router 3 is routing this way, And router 4 is also routing that way. So based on the path selection, let's say we choose router 1 as the exit point.
Okay.
When this goes down, what router 3 is going to do is to send update messages about every route that it received previously from router 1, and inside the update messages, these go in the withdraw field. Saying to router 4, I no longer have this path as valid. Router 4 would then delete these from the BGP table and then update the path selection to go that way. But you still have to run the path selection for every route. So it generally takes more time to converge because there's so many routes in BGP compared to IGP.
So router 4 received that update, the withdraw.
It receives the withdraw from its internal neighbor, correct?
So it received that.
Right,
But router 4 also did have a backup route
right.
to that destination. Well, does it need to wait for the update, or?
It depends on which path it's routing out to begin with.
I'm assuming the same route that you just drawn.
If they both agree to route this direction,
Yeah.
and we're going to go over this in detail, but basically what happens is that, let's say there's some route we're trying to reach A. It's one destination, but there's two routes to it. So we have route A1 and A2. It's talking about the same prefix. Maybe the prefix is 10.0.0.0/24, but the attributes of the route are different. This one says it's coming from 1. This one says it's coming from 2. 3 is going to take this and advertise it to 4. 4 is going to take its route and advertise it to 3. One of these is going to be chosen. One of them is going to be denied. So let's assume that router 3 says, I want this one. If router 4 says, I want this one, it means that this advertisement gets withdrawn. So now router 3 says, I only have one path to the destination. It knows only about A1. It doesn't know that this is an alternate route. So what you would see is that when we look at the BGP table, router 3 would only have one route for all the destinations. Router 4 is going to have multiple routes. You'd see that in the topology table, right? When we say show IP BGP, different routers are going to have different views of the network. Because the idea is that if you advertise me a route and I'm using it, I can't advertise you that same route back. So it's kind of a split horizon like logic, that if I want to make sure that we don't end up pointing the traffic at each other, so to do this, that if I'm routing through you, I'm just not going to advertise that same route back to you. But the problem you run into is that when the network has to reconverge, if this route goes away, the only way I can reconverge is to tell 4 that this route went away. That's with the withdraw. Then router 4 says, this is the only path that's valid, so I'm going to run path selection on those and install it, and now send an update to 3 saying you now have an alternate path of A2, but this is going to take some time to do it.
Does it happen immediately after I receive the withdrawal?
Happens immediately, right.
So it's like the feasible successor, where you have both routes in your table?
No, you still have to run the path selection.
Oh, you still have to run.
You still have to run the path selection. So when we actually do this and look at the failure, you can see in the debug output, the router chooses which routes it's going to use now. You can end up in cases where you learn the route, but you don't actually use it, and that's going to be the result of the best path selection.
Okay, well, there's a follow-up question, but just keep it in mind for now, you don't have to answer it. Can we do a load balancing in this scenario between the two routers?
In very corner case scenarios, you can. The vast majority of time, BGP will only allow you to use one path. But we'll talk about that when we get to some of these more examples. So in the meantime, let's take about a 10-minute break. When we come back, then we're going to talk about the different types of peers and how you actually build the design of the peerings.